Okay, we're starting the streaming, the live streaming. Once it's done, I'm going to start with the introduction. All right, this is Adrian Fagin, welcoming you to our Quantum Matter seminar. Today we have an exceptional Quantum Matter seminar with an exceptional speaker. Our guest is Dragana Popovic from Florida State University and the Magnet Lab in Tallahassee. And she's going to be giving us our first experimental talk. I'm very excited about it because it's about competing phases in high-temperature superconductors. Thank you, Dragana, for being here with us, and please go ahead.
Thank you, Adrian. Thank you for inviting me. It's a great pleasure to participate in this seminar series. I would also like to thank everyone who is joining us here today. So I'm also very happy to have the opportunity to give the first experimental talk, as Adrian said, and in particular, I will describe some results that we have obtained based on several years of experiments on cuprates at high magnetic fields in Tallahassee, Florida. So this work was done by both former and current members of the group. Zhenzhong Shi, who is now a postdoc at Duke, played a key role. Paul Beatty is now a postdoc in Glasgow. Jasminka Terzic is a postdoc at the Magnet Lab. Of course, none of this would have been possible without truly excellent single crystals that were grown by Takao Sasagawa, who is at the Tokyo Institute of Technology, and without the support from the Magnet Lab and the NSF. So it is well known that in cuprates, high temperature superconductivity, shown by this green dome, emerges by doping pairing compounds, which are antiferromagnetic multi-insulators. Cuprates are layered materials consisting of copper-oxygen planes with very weak interlayer coupling, so they behave in many ways as effectively 2D systems. Even though cuprates have been studied for decades in great detail, there are still many key questions that remain open, both regarding the nature of the superconductivity and the many unusual properties that these materials exhibit in the so-called normal state, that is, at temperatures above Tc. One key question is the nature of the ground state that would have appeared had superconductivity not intervened. So normally high magnetic fields are applied to suppress superconductivity and to expose the properties of the normal state. Another long-standing mystery, of course, is the origin of this pseudo-gap regime. Also in recent years, there has been a lot of effort on trying to understand the role of charge orders, which are now established to appear in all hold-up cuprates, and they're most pronounced around 1/8 doping, where Tc is suppressed. This interest was largely driven by the possibility that the vanishing of charge orders at high doping may be related to these putative quantum critical points that may be responsible for the behavior of the material in this cone-shaped strange metal region. In addition to charge orders, there are also other orders. For example, spin orders have been known from very early on. In some materials, like lanthanum 214 family, they coexist with charge orders. In particular, in these materials from that family, they are strongly intertwined. In each copper-oxygen plane, charge and spin orders appear in the form of stripes. So here is a sketch of one plane. So charge stripes are separated by whole poor antiferromagnetically ordered spin stripes. So the stripe correlations are strongest at 1A doping, where Tc is very suppressed, as you can see here, to very low values of only a few Kelvin. Now, in some other materials, such as YBCO, the situation is slightly different. For example, here it is known that charge order is stabilized only if magnetic field is sufficiently high to sufficiently suppress superconductivity. And spin order actually disappears at relatively low doping, so that spin and charge orders in YBCO do not seem to coexist. So in general, this pseudo-gap regime is known to be unstable towards a variety of ordering phenomena. So the competition between different degrees of freedom may give rise to various exotic states, including paired density wave, in which the superconducting order parameter is oscillatory in space with a zero spatial average. There is a very recent, very nice detailed review of the experimental and theoretical work on paired density wave in cuprates and beyond that appeared, I think, just a few months ago by Daniel Achterberg and others. Nevertheless, in spite of all that work, the evidence for a paired density wave in cuprates has been inconclusive, and even more importantly, its broad relevance to cuprate physics is an open question. For example, it has been suggested that actually it is the paired density wave that is responsible for the pseudo gap, and that all other orders, such as charge order, are subdominant. So in order to distinguish between different scenarios, the most intriguing question is what happens in the limit of zero temperature when superconductivity is suppressed? What is the ground state? So this is the question that we want to address. What is the ground state when superconductivity is removed? And we also want to be able to detect signatures of the paired density wave in that regime. So paired density wave, actually, it was shown quite some time ago in this paper here that in the presence of stripe order, it may be a ground state or very close in energy to the ground state. So here again is the sketch of charge and spin stripes, and the bottom panel shows the superconducting order parameter, which is most pronounced in charge stripes, but the phase is reversed between adjacent charge stripes. So this paired density wave, or the anti-phase superconducting order, was invoked later on in this paper by Berg and others to describe some surprising experiments on LBCO at 1A doping, a material which has a stripe order. So in particular, they found an unusual anisotropy in the they found that once charge and spin stripes are established, the in-plane resistivity shows a strong drop of an order of magnitude, but the out-of-plane resistivity continues to increase. The in-plane resistivity later goes to zero in a manner that is consistent with the Brzezinski-Kosterlitz-Towles transition, in other words, with a superconducting transition in 2D, but the 3D uniform superconducting order is established at an even lower temperature. There have been other experiments, many other experiments done on this material, and it is now generally agreed and accepted that this initial drop of the in-plane resistivity corresponds to the onset of a superconducting correlations in the planes. So in these striped cuprates, stripes are actually rotated by 90 degrees from plane to plane. So in this paper, they show that the presence of paired density wave in such an orthogonally stacked striped system leads to the frustration of the interlayer Josephson coupling and therefore to the layer decoupling. So the experiments were consistent with this picture. In addition to this work by John Tranquade and his group, there was another paper, earlier paper, in which they used the material from the same family and they changed the doping, and they found again that as the material was tuned into this regime with stripes, the interlayer Josephson coupling was reduced. For samples that were away from 1A doping, and I mentioned this because this effect is supposed to be most pronounced at 1A doping, and it should be less pronounced also with the increasing disorder. So here, there were also experiments done on materials that were away at 1A doping, from 1A doping, but it was found that in the presence of a perpendicular magnetic field, which stabilizes spin stripes, they were also able to find evidence for the suppression of the interlayer Josephson coupling. So all of these experiments were done on the lanthanum 214 family, and more recently there has been STM work in Seamus Davis's group on Viscous, in which they found evidence consistent with the presence of paired density waves. So this was done in zero magnetic field. So even though all of these data are consistent with the presence of a paired density wave, it has been argued that other interpretations might be possible. So in more recent years, people have also focused on actually trying to test and confirm theoretical predictions, which are, for example, listed in this nice review paper here. One such prediction was that in the presence of both uniform and paired density wave orders, it should be possible to detect another component of the charge order modulation. So this was done again by, found by STM in Viscous, where they applied a relatively small magnetic field such that the material was still in the vortex solid regime, but magnetic field was sufficient to suppress the uniform superconductivity in vortex halos and to allow the paired density wave order to emerge. Another prediction was for the existence of the so-called charge 4E condensate, and this was also observed recently in the group of Dale van Harlingen in Josephson junction devices made out of based on lanthanum LBCO at 1,8 doping. And yet another theoretical prediction was to actually probe the interlayer frustration by applying a suitable perturbation. So in these lanthanum 214 cuprates with stripes, it turns out that an in-plane magnetic field is actually a suitable perturbation because it is known that a sufficiently high field can lead to a spin-flop transition in every other plane. In other words, a sufficiently high parallel magnetic field will reorient the spin stripes in every other plane, and within the paired density wave picture, this should reduce the frustration of the interlayer Josephson coupling, and therefore the anisotropy should be reduced. So this is exactly what we tested and what we observed, as you will see. So to do these experiments, we chose these two materials from the same family, europium and neodymium co-doped LSCO. They have the same structure as LBCO. They're well known to exhibit a stripe order near 1,8 doping. These are their temperature doping phase diagrams with the data points extracted from the literature. So the vertical lines here show the doping levels of the two crystals that we studied. LNSCO was at 12% doping or 1/8. So here TC was very low. You can see it's very suppressed down to less than 4 Kelvin. And by the way, we define TC as the temperature where the in-plane resistivity goes to 0, or in other words, where it falls below the experimental noise floor. In LESCO, the doping was somewhat lower, 10%. So here the stripe correlations are weaker and TC is somewhat higher. These TCs are much lower than the temperatures where stripes are established. And they're also much lower than the pseudogap temperatures for these materials. So basically what we need to do now is apply magnetic field, suppress the superconductivity, and study the anisotropy by applying that suitable perturbation or parallel magnetic field. However, this is actually easier said than done because this means that we need to know when the superconductivity is actually fully suppressed. We need to know the upper critical field. And it turns out that this has been a highly controversial subject for decades in cuprates, and the interpretation of the experiment has been contradictory. To illustrate this problem, here are some examples, couple of examples from relatively recent papers that report measurements on exactly the same material, YBCO, at exactly the same doping, but the conclusions that were reached were very different. Here, for example, it was argued that the upper critical field is basically the same as the quantum melting field of the vortex solid. In other words, that in the limit of low temperatures, there is no vortex liquid. And here it was argued just the opposite, that actually the experimentally accessible magnetic fields are not high enough to suppress superconductivity, that the vortex liquid extends to much higher fields way beyond this quantum melting field of the vortex solid. So in order to actually address the question that we are interested in, we actually first need to resolve this issue. So after this introduction, the first part of the remainder of my talk will actually focus on trying to understand how a magnetic field destroys the superconductivity, and we want to map out the vortex phase diagram as a function of temperature and field. And for that purpose, we also use nonlinear transport measurements in addition to linear transport, because nonlinear transport is a direct probe of vortex matter. And then in the rest of the talk, I will focus on our evidence for a pair density wave, presence of the pair density wave in these materials. So first I will start with linear transport, and I can only, of course, show you a fraction of our measurement results. So I will focus on LASCO here. And so we are focusing first on the in-plane resistivity in the limit of zero current. So here is the dependence of the in-plane resistivity on the perpendicular magnetic field at different temperatures. At high temperatures, there is essentially no dependence on the field, or it's very weak because we are in the normal state. As we reduce the temperature, one starts seeing positive magnetoresistance, which is well understood to result from the suppression of superconducting fluctuations. And as we reduce the temperature further, then we start seeing a peak actually in the magnetoresistance, which becomes very sharp at very low temperatures, followed by this wide region of negative magnetoresistance. So this was actually quite surprising, because a peak in the magnetoresistance of cuprates had not been observed before, even after all these decades of work. So we also see that the position of the peak shifts with temperature, and it seems that it represents some kind of characteristic energy scale. So we decided to track that. And from this, you can also extract the temperature dependence of the resistivity for different magnetic fields. And here we are showing all the results up to 18 Tesla for clarity. So from here, obviously, you can determine TC. You see that as you increase the field, TC is suppressed, as you would expect. And we also notice that once TC goes to zero, we start seeing a peak in the temperature dependence. So some curves that wanted to be insulating like, they actually at lower temperatures turn down in a metallic-like or superconducting-like fashion. And this position of the peak also shifts with the field, so we decided to track that. So in addition to this linear transport, as I said, we measured nonlinear transport, in particular differential resistance as a function of the applied DC current. So here are the results shown for one fixed low temperature for different magnetic fields. The bottom trace corresponds to the case when we are below TC. We are in the vortex solid, and this is why we are measuring zero resistance, and the applied current is still below the critical current. So this is what's expected. And then we keep increasing the field. TC is suppressed to zero, but what we find over a wide range of fields, that even though resistance in the limits of zero excitation is finite, the resistance depends on the current applied. And this is actually exactly what is expected for a vortex liquid, that is for vortices that are moving in the presence of disorder. We can keep increasing the field further, and eventually at some point you get to the field where transport becomes ohmic. It doesn't depend on the applied current, so you can in this way determine this field that we label H star, which represents the boundary between this non-ohmic and ohmic transport. So based on what I already described, you can construct the vortex phase diagrams for these materials, and this is shown on this slide. So here TCs are shown with these black symbols. You can see in both materials, TC is suppressed to zero, but relatively low field of only about 5 Tesla. So this is the quantum melting field of the vortex solid. Maybe I should use a laser pointer. Okay, so this is the quantum melting field of the vortex solid. The green symbols represent the positions of the peak in the magnetoresistance at different temperatures, and these red symbols represent the boundary between non-ohmic and ohmic regimes. And finally, the blue open diamonds are the positions of the peak in the temperature dependence. So below this peak, we have metallic or superconducting light behavior, the drop of resistivity with decreasing temperature. And outside of this region, we have insulating-like behavior. So what we see here is that there is a wide range of fields of 15 or 20 Tesla that separates this vortex solid from the high field normal state. So what does exactly the behavior of the system look like in this intermediate regime that we are calling viscous vortex liquid? Well, the linear resistance, it turns out, is described best phenomenologically with a simple power law, as you can see here on this log-log plot. And this means that as temperature goes to zero, resistance goes to zero. In other words, the material becomes a superconductor at zero temperature. And as I already showed you, the transport is also non-ohmic. This is just one example. So again, even though the linear resistance is finite in the limit of zero current, so these points correspond to these points here, we see that for all other currents, the resistance actually depends on the applied current, which is what one expects for the vortices that are moving in the presence of disorder. So basically, as we reduce the temperature, the vortex liquid slows down and becomes more sluggish, more viscous. This is why the resistance drops, and eventually they freeze at zero temperature, so material is a superconductor. And the existence of power laws is actually consistent with the proximity to this phase transition. So in addition, at these high temperatures in this regime here, we have ohmic transport, but this is a bosonic regime. We have positive magnetoresistance. So we identify this as the vortex liquid. So basically in this phase diagram, what this phase diagram is telling us is what essentially you would expect. At high enough temperatures, thermal fluctuations melt the vortex solid into vortex liquid. As you reduce the temperature, thermal fluctuations become less relevant. Vortices start to feel the effects of disorder, their motion slows down, and the resistivity drops, eventually goes to zero, and it freezes into vortex glass at zero temperature. So what we see here also is that all these different really energy scales coincide, and it seems that this field here, 20 Tesla in this material, corresponds to the upper critical field. This is where superconductivity with vortices vanishes. We also looked at the magnetoresistance at high temperatures in a standard way, and these open dots represent the onset of superconducting Gaussian superconducting fluctuations, and they actually extrapolate in the zero temperature limit to the same field, supporting our conclusion that this is the upper critical field in these materials. Also, at zero field, what we see is that the onset of phase fluctuations is at temperatures that are several times higher than TC. And this is actually consistent with the findings of many other experiments using stereospectroscopic techniques, also on other families on cuprates. However, in these two materials, this is still a temperature that is much lower than the pseudo-gap temperature. So at least in these measurements, we do not see evidence for pairing at temperatures that are comparable to the pseudo-gap temperature. There are a couple of other things that I would like to point out. So as I said, it's interesting that a peak in the magnetoresistance, at least at low temperatures, seems to correspond to the field scale for closing of the superconducting gap. And it is also peculiar that its position has this non-monotonic dependence on temperature. We do not understand the origin of that, but it is actually very similar to the solid liquid melting line in the temperature pressure phase diagram of helium-3 that was predicted by Pomeranchuk. So one might speculate this indicates that the entropy in this stripy normal state is higher than in the vortex liquids, which may be not so surprising. But in any case, we are not at this point, we do not know whether this boundary represents a true phase transition or this is just a crossover. Also, the upper critical fields that we found here is actually significantly higher than what was claimed in previous studies on these same materials that have been conducted at higher temperatures. For example, in LESCO, the study was down to 1.5 Kelvin and up to lower fields. So it was concluded that the upper critical field was about 8 Tesla. So perhaps if we had limited our study to such a narrow range of parameters, we might have reached the same conclusion. But what this also shows is that it is necessary to go to temperatures that are orders of magnitude lower than the zero field TC in order to make reliable extrapolations to zero temperature. And of course, one needs to, in transport measurements in particular, be very careful with current excitations and conduct nonlinear transport measurements. Also, these two phase diagrams are obviously they're qualitatively the same, even though the strength of stripe correlations is different. But it is also qualitatively the same as what we had found some years ago in highly underdoped LSCO, in which no charge orders have been reported, or if there are any, it must be at best very weak. So this is just a sketch from that paper, but basically shows again that the melting field of the vortex solid, shown with this dark blue region, is separated from the high field normal state by this wide range of fields where we find power law, temperature dependence, with resistance going to zero in the zero temperature limit. So what this means is that the vortex phase diagram is not affected, is not very sensitive to the details of competing charge orders. It is qualitatively the same regardless of the presence or the strength of charge order. On the other hand, what is important are quantum fluctuations and disorder in the limit of low temperatures. And these are based on general arguments. One expects that this should be also relevant to other families of cuprates, and I'll come back to this near the end of the talk. So now that we have established these phase diagrams, what we actually want to do now is address our main question. And this is, we want to look for the evidence of pair density waves. So we want to focus on the study of the anisotropy or anisotropy ratio, which is the ratio of the outer plane to the in-plane resistivity. So here are results again on LESCO in zero magnetic field. On top, we see that the in-plane resistivity shown by this red curve has this drop. However, the outer plane resistivity continues to increase, and they both go to zero at the same temperature, same lower temperature. So in the place where this in-plane resistivity exhibits a drop, the anisotropy has this enhancement, this kind of bump. And this is actually the same thing that was observed in LBCO. This is this paper by John Tronquada's group that I discussed at the very beginning. Here, the in-plane resistivity is shown on a log scale, so you can see the initial drop maybe more clearly, followed by the final drop of resistivity. And on the top, this is the anisotropy, again, on a log scale. So this enhancement of the anisotropy, this initial bump, is really related to this drop of the resistivity, which is understood, at least in LBCO, to represent the onset of superconducting correlations in the planes. So we conclude that probably the same physics is taking place in our two materials. Here we want to go one step further and actually study the evolution of this anisotropy first with a perpendicular magnetic field as we go through our phase diagram. So here on the left, these are the zero field data for comparison. On the right, in the main plot, we have an anisotropy ratio as a function of perpendicular field at different temperatures. So at high temperature of about 20 Kelvin, we do not see any field dependence, which is what you would expect because we are in the normal state. However, as you reduce the temperature, we start seeing this very non-monotonic behavior. And for example, let us focus on the lowest temperature, 70 millikelvin. These are these black symbols. So as we increase the perpendicular field, the anisotropy ratio increases by more than an order of magnitude. So clearly the planes are getting decoupled by the magnetic field. As we increase the field further, the anisotropy drops. We are left with fluctuating superconductivity in the planes. And eventually at high enough field, the anisotropy no longer depends on the field, and it's comparable to the value we had at high temperature. So this is what you expect in the normal state. So this happens in this material at fields above 20 Tesla, which is exactly the upper critical field that we had identified based on those other measurements that I showed you earlier. So this supports our conclusion that this is the upper critical field. So if you look at this curve and that curve, you can see that they're similar. So what this is telling us is that the behavior is the same as we approach the superconducting transition, either by reducing the temperature in a zero magnetic field or by reducing the magnetic field at a fixed temperature. So in both cases, we see this enhancement of the anisotropy. So we again interpret this as the onset of superconducting correlations in the planes. These same data are shown here on the left. So the color map represents this anisotropy ratio. And here we have some familiar data points from our vortex phase diagram. In particular, black symbols are values of Tc. Green symbols are the positions of the peak in the magnetoresistance that we identified with the upper critical field. So indeed, you can see that as we reduce the field below the upper critical field, the anisotropy ratio starts to increase. It's enhanced around this field where we see a bump in these 2D plots. And in addition, we also have these pink symbols that represent the layer decoupling field. You can see a huge enhancement of the anisotropy there. So in LNSCO, which is at 1A doping, the situation is qualitatively the same. You can see the same enhancement. You can see this light blue band here, the enhancement of the anisotropy as the field is reduced from the normal state below the upper critical field. The only difference here is that this decoupling field basically coincides with the TC, because this system is already at 1/8, it's fully frustrated, and this is precisely what is expected within this pair density wave picture. So it is also helpful, I think, to compare the behavior of the anisotropy ratio to the temperature dependence of the in-plane resistivity for different fields. Here we have, so again, we are showing so these curves correspond to different magnetic fields. Temperature is on a log scale, so you can see the lower temperature behavior better. And this dashed line connects these kinks, these initial drops of the in-plane resistivity. So this is where the anisotropy is enhanced. And the dashed line here for this material shows where the layer decoupling field is. And as I said in LNSCO, it basically coincides with the TC. So what this means is that essentially, or almost all of the data shown on these two plots are describing the 2D physics, the physics of copper oxygen planes. And piece of evidence, an interesting observation that supports this conclusion is the fact that these curves separate into two families. One family that wants to become superconducting, another one that does not. Exactly when the sheet resistance is basically the same as H/4E squared, which is the quantum resistance of Cooper pairs. And this is precisely what you would expect for a 2D superconductor insulator transition that is driven by quantum phase fluctuations. There is another similarity to other 2D superconducting systems that I would like to emphasize at this point, and this is the existence of this two-step transition. This is something that is actually very well known in various granular films of conventional superconductors. It has also been seen in relatively clean heavy fermion and iron-based superconductors with competing orders, but I think it is best understood based on these Josephson junction arrays that have been engineered by depositing islands of conventional superconductors such as niobium or tin on various substrates such as gold or graphene. So it is well understood from those studies that this initial drop of the resistivity actually corresponds to the onset of local phase coherence in the islands, and the TC, where resistance goes to 0, corresponds to the onset of the global phase coherence in the entire film. So in analogy to that, it seems plausible that this initial drop of the in-plane resistivity, where superconducting correlations start to set in the planes, we have some kind of superconducting islands or puddles. And in the same analogy, at low temperatures, as we increase the field, it seems that this happens, that the destruction of superconductivity in the planes occurs by quantum phase fluctuations of these Josephson-coupled superconducting islands, and then at even higher fields, eventually the superconductivity in the planes is destroyed. So in hindsight, this is actually maybe not so surprising, because these materials are intrinsically granular. There is a nanoscale phase separation. We have charge and spin stripes, and they do not span the entire sample, but they do have a finite correlation length, which is of the order of 100 angstrom. So, and it's also interesting, this kind of possibility was mentioned very briefly at the end of this review paper on failed superconductors, where they said near the end that maybe in these cuprates with stripes, these cuprates with stripes may give rise to some kind of intrinsically granular superconducting state. So our findings so far can be summarized, I think, in this sketch. So this is a phase diagram on a linear scale. This is why the curvature of these lines is different from what I showed you before. So basically, what we have found so far is consistent with the presence of local pair density wave correlations in superconducting islands or puddles above TC in 0 field. But as we reduce temperature, the uniform superconductivity dominates. However, as we increase the magnetic field, we destroy the superconductivity, and we find evidence for layer decoupling and for pair density wave when this, again, when uniform superconductivity is sufficiently suppressed beyond the quantum melting field of the vortex solid in the regime of strong superconducting phase fluctuations. And as I said, as we increase the field, the system breaks up into superconducting puddles, and eventually even higher field will destroy the superconductivity in the puddles. However, so the data are consistent with the pair density wave picture, but the true test really is the application of a suitable perturbation of an in-plane magnetic field, which within the pair density wave picture should frustrate the interlayer Josephson coupling, reduce the frustration and reduce the anisotropy. So in practice, what we do is we rotate the sample in the magnetic field, and from the total field applied and the angle, we can obviously calculate the perpendicular parallel field components, and we can extract the values of the in-plane and out-of-plane resistivities for a particular combination of perpendicular and parallel fields. So what we want to do really is we want to look at the anisotropy as a function of first of the perpendicular field. In other words, we want to see what it's like in different parts of this vortex phase diagram, which is what is shown here at a fixed temperature. So we are going this way. And in addition, we have a parallel field component or a magnetic field in the plane also, as given here. So first of all, what we see at the highest fields, we do not see any effect of the parallel magnetic field, which supports our earlier conclusion that in this region, there is no evidence from our experiments, at least, for a continued presence of Cooper pairs. So it seems that this indeed is the upper critical field. However, between the layer decoupling field and the upper critical field, we see that the anisotropy ratio decreases exactly as predicted in the pair density wave scenario. This is maybe not so easy to see on this main plot because this is a log scale, and this is why we have this inset, which is a blow up of this region close to the upper critical field. And the smaller inset is a blow up of this region near the peak, near the decoupling field. So here in the peak region, for the range of parallel fields that were accessible, the anisotropy was reduced by about 6,000. So that's a 10%. The anisotropy here is really huge. So this confirms this scenario, and it seems consistent with this mechanism of the reorientation of stripes by the parallel field. But in order to try to understand the effect of the parallel field better, we also looked at its effect on the in-plane and out-of-plane resistivities separately. So here on the top graph, this is the relative change of the in-plane resistivity with respect to its value with 0 applied field. So these are the values of the parallel field. And again, as a function of as we go through our vortex phase diagram, as a function of a perpendicular field. I hope this is clear. So basically what we see is that the parallel field always reduces the in-plane component. And this is the opposite of what we would expect if the dominant effect of the parallel field was to break up the Cooper pairs. And in fact, if you look at here, I mean, this effect of the parallel field is stronger in the region where superconductivity is weaker. So it seems that the dominant effect of the parallel field is not related to superconductivity. And in fact, it's most pronounced in the regions where we observe some hysteretic behavior in the magnetoresistance that I didn't have time to discuss, but which is consistent with the presence of domains of spin stripes. So we conclude that the dominant effect of the parallel magnetic field is the reorientation of the spin stripes. So in that case, one expects, as I said already several times, that the frustration of the interlayer Josephson coupling will be reduced within the pair density wave picture. We should reduce the out-of-plane resistance, and this is exactly what we see. And the effect on the out-of-plane resistance is stronger, so the overall anisotropy is reduced. And we see also qualitatively the same behavior on LNSCO. We have repeated this also at many different temperatures. And here again, I'm using the sketch to show you the range of parameters where we see the effect of parallel magnetic field or the evidence for a pair density wave. So this is shown by this hatched region here. Basically, the effect of parallel field is seen all the way up to temperatures where magnetoresistance in transport, the peak in the magnetoresistance vanishes. So we see that, again, we see the effect, evidence for pair density wave when planes are decoupled, when we have a fluctuating superconductivity in the planes. In other words, when we have many vortices. So from that point of view, this is consistent with the STM evidence for a pair density wave in vortex halos in Viscous. The extent of the observation of the effect of the parallel field or the evidence for pair density wave extends to temperatures that are several times higher than TC, basically up to temperatures where we see the onset of phase fluctuations. And as I said before, this is a much lower temperature in these materials than the pseudogap temperature. And we also do not see any evidence for a pair density wave for fields that are higher than the critical field. So our results do not support a scenario, or do not support a scenario in which the pair density wave correlations are responsible for the pseudogap. So what we have established is, I think, a robust vortex phase diagram for underdog cuprates. It is really determined by quantum phase fluctuations, disorder. It is not sensitive to other orders. Our work was done on LESCO, LNSCO. Also, I mentioned our earlier work on LSCO. Also, recently, we worked with a group of John Tranquada on LBCO, and also found evidence that superconducting correlations persist even beyond the melting field of the vortex solid. So based on all this and general arguments, again, we expect the same thing to be seen in other cuprates. In YBCO, for example, as I showed at the beginning, there have been reports or claims that the vortex liquid does persist at very low temperatures. And concerning transport, I know that Suchitra Sebastian has reported some transport measurements at conferences where resistance, about the regime of fields where resistance depends on the applied current. And this was discussed in terms of fragile superconductivity by Steve Kilson, for example. But this is, I want to emphasize that this is precisely what you expect in the vortex liquid regime. So to me, at least, it seems that this is something that's not really specific to cuprates. This is what you would expect for all type 2 superconductors that are reasonably clean. Nevertheless, it is, I think, very important to pursue similar studies in other cuprate families. And indeed, we have been already performed a series of measurements of bismuth 2201. This is work that is still unpublished. Hopefully it will be written up soon, but basically those results also support our conclusions that I showed you here. So now that we know what the upper critical field is, we can really go after problems that may be more interesting, that were our original goal, which is to try to understand the nature of the high field ground states. And so far, we have performed some Hall effect measurements on these materials with stripes that have given us some intriguing results, and that also call for additional experiments by other kinds of techniques at high magnetic fields. I also showed you evidence results that confirm a theoretical prediction. So it seems that these materials do really host a paired density wave. However, even though this does not seem to be a so-called mother state or responsible for the pseudo gap in these materials, it is obviously important also to probe other cuprates in the regime, high field regime, beyond the melting field of the vortex solid. And I know there have been some such efforts so far, but this work is still ongoing. So I would like to, that's all I was planning to say, and I would like to thank you for your attention again.
Thank you, Dragana, for such a beautiful talk and amazing results. Very impressive. I think I thank you, representing all the people in the audience. Now I'd like to welcome the audience to raise their hands and ask questions, or use the chat window to post their questions, and I'll read them to the speaker. I have a very naive question. This is related to the one of the items here in your summary. Is it known what's the, maybe it's pretty naive, but do you know what the polarization or magnetization of the sample is at 20 Tesla?
At 20 Tesla, we did do the measurements. I mean, one problem or complication, we have done those measurements, but in these materials, it is the rare earth ion that dominates the magnetization, in contrast to the copper spin moments. So yeah, so it has been studied, but it's very challenging to try to separate it. And there have been some experiments in the past, primarily by Markus Hicker, who was able to determine and subtract the defects of the rare earth. For example, one flag paramagnetism, europium, neodymium has ferromagnetic tendencies. So yeah, I don't have the answer for, say, copper moments, and also these studies have really not been done at very low temperatures. They're typically done down to 4 Kelvin or so. So there have been no probes in this regime. We have done some torque magnetometry measurements from which we are able to see that the TC coincides with that you obtain from transport, but it's really hard to tell anything about what happens at higher fields because, again, because the signal is dominated by these rare earth ions.
I see. I understand. And concerning the nature of the normal state or the actual mother state,
yeah,
you mentioned this reference with some surprising
right.
results. So can you maybe walk us briefly through the main conclusions of that work?
So well, in the high field normal state, what we found, first of all, for the temperature dependence of the in-plane resistivity is that it is insulating like, it seems most likely like a logarithmic temperature dependence, similar to what had been observed very early on in LSCO by Ando and Bobinger. What is different here is that as we keep increasing the field, this weak insulating like dependence is actually suppressed. And it seems that the high field normal state is a metal, and this is actually described in this first paper here. Now, this reference from the Hall effect, it finds that in this high field regime, above the upper critical field, the Hall coefficient essentially vanishes over a wide range of temperatures and magnetic fields in the phase diagram. So the question is why? I mean, from the measurements that we have, there is no evidence for any Cooper pairs that may persist at such high fields, and also other kinds of measurements on these materials. For example, determine the spin gap, found that it's very low, so not more than 1 milli-electron volt, maybe 2. So there is no evidence for that. So that's the main question. Why does the Hall coefficient vanish? So, I mean, we have data, obviously, for the Hall effect at lower fields, and we show that in these two materials, it's again largely dominated by vortex physics. But again, the question is, what is the origin of that? So there are several possibilities, but in principle, it is in standard models, Hall coefficient can vanish only accidentally if you have cancellation for a given temperature and field. So what's peculiar is that this happens over a wide range of fields and temperatures. So we do not know what the origin of this is. It is certainly a new and very intriguing property of this high field normal state, which should be also probed by other techniques and in this high field regime. So that's almost a separate talk, but basically, yeah, I didn't want to cram too much information here.
No, this is perfect. Yeah. Thank you. So concerning, I have another question. I'm waiting for the audience to participate. So if you have any questions, please raise your hands or post a question on the chat. So I'm just curious. In the phase right below, in the regime right below the upper critical field, when you apply a perpendicular, a transverse magnetic field or parallel magnetic field, I'm just wondering, would you be able to identify or sort of well, I'm thinking in the context of FFLO physics, full depth
Right,
field,
right.
in which you have a partially polarized sample and you have an order parameter that resembles a pair density wave. So I'm just wondering whether you wouldn't get similar results in your experiments if you had FFLO physics, or it would differ. You can actually sort of
okay, so right, so that's in
distinguish
a
one from the other.
ferromagnetic field. This is purely Zeeman effect, right?
Right.
So in this range of fields, the parallel field does not really do anything. I mean, the resistance is still zero in this range of fields here. So yeah, but you mean in principle? Well, what exactly would one be testing? I would have to think about this. I mean, yeah. So I mean, this is just a
maybe
yeah.
I'm being.
So this is just a Zeeman effect, and so I mean here, okay, maybe we would have expected to see something here, and I think I try to kind of discuss that here. Basically, what is the effect of the parallel field? Is it mainly to destroy Cooper pairs, or it's something else? So it seems that it's something else that dominates. So if that effect exists, we cannot see it here. But also, okay, I'm not a theorist, and I think there is these are not quite the same. I mean, this is I'm not sure whether that picture is appropriate. I mean, this is certainly one FFLO is like a special case of pair density wave. That's what I've heard, but again, I'm I'm not able to discuss it really. But I don't think that effect is really dominant here, the Zeeman effect.
All right. Well, it seems that we don't have any other questions. So
well, okay, thank you for all of your questions.
Thank you so much for your talk and
thanks for having me,
joining us. And you guys in the audience can review the talk on YouTube. If you have any pressing questions, maybe we can redirect them to Dragana. Thank you so much, and see you on Wednesday for our next experimental talk.
Okay, thank you. Bye.